There are multiple ways to change the phase of matter of a substance. You can either change its temperature or change its pressure. And you can view this relationship between pressure and temperature on the phase of matter of a substance by looking at a phase diagram. Although this may seem complicated at first, it's actually very simple. So first, let's look when a substance is a solid. So what you'll notice is that solid, which is everything to the left of this line right here, has a low temperature. And this makes sense. For example, when water, which is a substance that we can use in this phase diagram, has a low temperature, its particles lose kinetic energy and it becomes a solid. It becomes solid ice. We can also see that solids have a high pressure. This also makes intuitive sense because if you have a lot of particles that are moving about and you increase the pressure on them, they become compact and they become a solid. Next, let's say we are over here and we increase the temperature. So the particles gain kinetic energy until they're no longer a solid. They reach this line, which indicates melting, and it becomes a liquid. Now, remember that liquids have a little bit more kinetic energy and they can flow, and this makes sense as they have a larger temperature. And we can also keep increasing this kinetic energy more and more and more until it crosses this line, which can be boiling point, we could say is this line, and it becomes a gas. This is when particles have the most kinetic energy. We can also think about changes on phase diagrams by looking at the graph vertically. So let's say, for example, we have a substance, let's go with water. It's all the way down here, it has a very low pressure. At this very low pressure, this substance is a gas. This makes sense as there's less force pushing the particles together and they're more likely to move around freely. So let's move up and start increasing the pressure. So we move up, and slowly the particles move together until we reach this line. Now remember that the phase change from a gas to solid is known as deposition. This can be seen in dry ice, for example. You should look it up if you can't really visualize this. But we can increase the pressure until all the particles get pushed together and sort of forced together until it becomes deposited into a solid. There are a few features regarding phase diagrams that you should know for a general chemistry class. The first is that this is a general phase diagram. Each substance, for example, water, carbon dioxide, nitrous oxide, they can all have different phase diagrams. However, the basic shape is the same. You will have solid, liquid, gas, and you will have all these different lines representing phase changes. Another thing you should be aware of is the triple point. At this point right here, solids, liquids, and gases can all coexist at the same time. So at this temperature and this pressure, you can have a block of ice, a glass of water, and some water vapor. And the same idea is true for these lines. So at this line, which indicates melting or freezing, you can have a block of ice or a glass of water at the same time. Another feature to be aware of is this point up here. This point is known as the critical point. At very high temperatures and very high pressures, the distinction between gas and liquid becomes kind of unclear. Particles and substances that are past this line at high temperatures and high pressures are known as supercritical fluids. At the critical point where critical temperature and critical pressure meet, a substance that has a large amount of kinetic energy cannot be compressed enough with enough pressure to act as a liquid. As a result, supercritical fluids show properties of both gases and liquids. Like a gas, supercritical fluids expand in order to fill its container. However, supercritical fluids have very high densities and almost flow and move like water. Like liquids, supercritical fluids can actually dissolve substances. However, because it's almost a gas, it can actually move through solid substances and dissolve soluble particles. This is why supercritical fluids are used in the process of creating decaffeinated coffee. Supercritical carbon dioxide can be used to penetrate the solid of a coffee bean and take out the caffeine, leaving decaffeinated coffee.